This is the last segment of logic design concepts. We have seen gates, we have seen flip-flops, we have seen combinational circuits, we have seen sequential circuits, we have seen buses, we have seen combinational upper-level components like adders, subtractors, and things. We have seen sequential upper-level components like shift registers, counters, and things. We have also seen controllers, or we have seen state machines that act as controllers. Okay, what we haven't done is we haven't put all of these together. What I'm doing now is I'm coming up with a complete RT level design, register transfer level design. What is a register transfer level design? In register transfer level, you will think at a higher level. You will take a, let's say, a divider. You want to divide some number by some number, and then how do you go about that? Do you do a state diagram? Do you do Carnot maps? Well, you cannot do those because those are very basic and they're good for small elements, but not for a system like a multiplier, a divider, or something like that. I'm not going to do a divider. I'm not going to do a multiplier. I'm not going to do a filter or anything. All I'm going to be doing is a very simple serial adder, one that takes inputs from its A and B, takes data inputs from its A and B inputs, clock by clock, and in 8 consecutive clocks, it will be adding those data together. And after 8 consecutive clocks, it will issue a ready signal, and it will generate the output, an 8-bit output. That was the problem statement. Okay, how do I go about this? Well, when you are doing an RT level design, okay, when you are doing an RT level design, let me use a color like this. Okay, RTL design. You first start with the problem description, and then you decide, okay, I need some data components. For example, if you're doing a multiplier, you say, well, multiplication is done by adding, so I need an adder. Okay, a combinational adder. Then you say, well, at one point I need to count some inputs, so you need a counter. Then you say, well, at one point for a filter, for example, you need to save some previous data, and then you need a register file. What is a register file? A register file is really a short memory. Okay? As you are deciding all of this, you are saying, well, the counter has to count when I tell it to, and also it has to reset when I tell it to. The adder sometimes adds, sometimes subtracts. The register file sometimes is written into, sometimes is read from. All of these red ones I'm marking become your control signals. Then you say, well, okay, then you say these are, the red ones are control signals, and the boxes here are my data path components. What are data path components? Well, any component that can process data, like add 2 pieces of data, compare 2 pieces of data, is a data path component. Any component that stores data, like a register file, a counter that holds data and start counting data, is a data path component, and also any component that transmits data. That means, for example, the buses that go back and forth between these components, those are also part of your data path. as you are designing your data path, you are also coming up with certain signals. For example, remember I had the signal for selecting a source of a bus. So you have also a signal for selecting sources of these buses. Okay? Maybe these buses are unidirectional, maybe they're bidirectional, but then in any case, you have situation where the buses may be going back to some other components, something like that, and therefore you are deciding on holders of data, register files, registers, and counters, processors of data, adders, subtractors, and also counter, because it takes the data and counts it up from that data, and also transmitters of data, that are the buses. As you are doing this, you are also coming up, like I said before, with signals that we call them control signals. Nobody so far has talked about how these control signals are being controlled, are being generated. This part here is the data path. I also have what is called the controller. The controller part of my RT level design is, this is controller. This is data path. The controller part of my RT level design is a part that takes input signals from the data path and from outside. For example, somebody tells it, okay, start doing the work. Someone tells it, start taking data from, let's say this is a multiplier, start taking data from the filter or something like that. And the controller here looks at these signals and then, based on the inputs that it receives, goes from one state to another. So what is the controller? Then the controller is a state machine. Not like those state machines that has one input and one output. It is a state machine that may have 10 inputs, 20 outputs. But again, basically the same thing as a state machine. It makes decisions, waits for inputs, and then issues certain signals. Waits for some other input, issues some other signals. It is in the start state, then it is in the processing state, then it is in the calculation state or something. As it passes through these states, it issues certain control signals. Okay? Just like the state machine that we showed before. It has a state diagram, but many states, many inputs, many outputs. These control signals that are issued, I'm showing them as red dots here, those are the control signals that are issued by my controller and are passed along to the data path. And therefore, the data path doesn't make decisions. The data path has signals that is waiting for decisions made in the control unit, and based on those decisions, things in the data path happen. The bulky part of my design is the data path, but the thinking part of my design is the controller. The controller and the data path components both have the same clock. Okay, so if I have a clock, my register file, my counter, that clock is the same clock as my controller. I also have a reset. This is the clock. This is the reset. Okay. And then maybe the reset is into my register file, also into my controller. So these signals, I'm showing the clock and the reset, are shared, and then events in the controller and events in the data path are synchronized. We will be doing a lot more RT level design in the various courses, but in this course here, in this review of logic, I just want to show you a very simple RTL design following this style that I'm showing you. Okay, a controller, certain control signals, certain data path signals. And the way I design is this: I start with the problem statement, and then I decide what part of it is my data path, what part of it is my controller, and then I do the data path design, and then I do the controller design. The example I'm using, like I said, is a serial adder, and it has a clock, it has a reset, it has a start input. After a start, it will start taking data from A and B. So data on A and B come in like this, synchronized with the clock. Okay, so there is this clock here, and therefore in 8 consecutive clocks after the start, data on A and B will be picked up, just like the X input in the state machine, in the state diagram, that state machine, the sequence detector, the X input in the sequence detector was going up and down, zeros and ones, and on the edge of the clock you pick up the proper data from the X inputs. Same thing over here. After you start, on the edges of the clock, you will be picking up your data from A and B, and in 8 consecutive clocks, least significant bits first, you will be adding them together. Once you have added them together, after 8 clocks, you will generate the add result, put it on the result, and issue the ready signal. Okay? With all this being said, let's decide what are my data path components, what are my control, and what are the signals. Okay, data is coming in bit by bit. Okay, they need to be added, and therefore let me clean this up. So I have some room to do my design. All right. So, data are coming in from here, from here. They need to be added. So what do I need? I need a full adder. Okay. The full adder creates the add result. If bit 0 and 0 are added on A and B, then the next one, let's look at this. 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1. I add these two together. 1, 0 is a 1, carry of 0. So the next bit requires the carry from the previous one. 0, 1, 0 is a 1, carry of 0. 0, 1, 1 is a 0, carry of 1. So I always have to keep the carry so that I can add it to the next bits coming in with the next clock. Okay, and therefore what I need is a flip-flop. Okay, so that this is the sum output, this is the carry output. The carry output gets into this, and actually 1D holds the carry so that I can use that carry for the next bit position. Okay. As the results are coming out, the first bit is ready, the second bit is ready, and therefore what I need is I need to put them inside a shift register. Okay, so as results come in, I need a shift register to store bits or shift my data to the right one bit at a time. Eventually, after 8 clock pulses, I have 8 bits of data here. That becomes my output result. Okay? These are my data path components. What I haven't said is, when do I clock the shift register? When do I enable its clocking? When do I what do I do with this flip-flop here? Do I clock it all the time, or do I reset it sometime? Well, I do need to reset it, because if I have done some adding and then the next new round of data comes in, I don't want to I don't want to use the carry from the previous time in this new round of data, and therefore this needs resetting. But then one thing I have decided is that my data path components are a full adder, a D flip-flop, and a shift register. Okay? And then I need my controller. My controller has signals coming in from this. Okay? Signals coming in from here. And my controller looks at the start, makes decision based on the start, keeps a count of how many times it has added, and then as it's adding, it issues a signal to the shift register to keep shifting. At the beginning, it issues a signal to my D flip-flop to reset, and when it's completed, it issues a signal on the ready that the adding has been done. Okay, so this is how my design is going to be. I'm going to have a data path. I'm going to have a controller. The data path has those 3 components. My data path has a signal called init coming from the controller, so that flip-flop, this flip-flop here, will be initialized to 0. My data path has a signal coming to it for shift enable. That means don't keep shifting all the time. Only shift when the controller tells you to. And then the controller has a start signal and a ready signal. Start and ready, even though they go to the whole serial adder, but they are really not a part of the data path of it. They are part of the controller. They directly come in to the controller, and the controller issues the ready altogether. So the initial partitioning is done, and this is my data path. Okay, this is just a little bit more detailed than what I showed here. Let's go over the details and let's show why we have everything that we have over here. The part on the left is the full adder, which is fine. Okay, this is the data path, the full adder. Okay, and you know what that is, right? It's a series, a couple of XORs in it, some AND gates, some OR gates, producing a S input and S output and a carry out output. And then I have this flip-flop here. The flip-flop is a flip-flop that takes the carry out and holds it in there. But then at the very beginning, I have to have a mechanism for resetting the flip-flop to 0. To do that, I have the init signal. The init signal comes in from the controller. If it's 1, it puts a 0 on the D input. So at the very beginning, puts a 0 on the D input. The clocking is done, and therefore a 0 goes into my flip-flop. And then therefore this is another one of my, actually this together with this is another one of my components. Okay, this flip-flop has synchronous reset input, which I'm calling it the init signal. The third component, and then now I decided that init is also a signal coming from the controller, okay, which in my first diagram I showed it as red, and therefore this is coming from the controller. Another controller, another data path component is this shift register. Does this shift register shift all the time? Well, it does take the serial input from the adder, okay? But then it doesn't shift all the time. It only shifts when my controller tells it to shift through use of this signal. What did I say about data path design? I said decide on your components. These are these yellow components. Decide on the signals that control these components. These are these red signals coming from the controller. And also decide on the busing of it, the interconnection of the components. Well, my design is so small that I really don't have a lot of buses. But then if for the sake of following the rules, this is a bus. This is a bus. This is the output bus. Okay, and this is also a bus connecting my flip-flop to the input of the full adder. I'm done with my data path design, and then I have to go on to my I'm just doing one more step for my data path. I said that full adder, you know what it is. The flip-flop, you know what it is. Shift register, you can either decide that, yeah, I know what the shift register is. Just put flip-flops next to each other. But then if you want to get more into the details of the shift register, well, this is more of a detail, more details of the shift register. The shift register either does nothing, okay, an 8-bit shift register. Let me show it here. Let me show only 4 bits of it. Multiplexers here. Remember when we talked about shift registers, we said that if you want to have a shift register that has several different things, we put multiplexers to decide what it does. And then feedback, 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 feedback from the previous bit, from the previous bit, from the previous bit, and this is serial in. Okay, and these multiplexers have a control input. If it's 0, it selects its upper input. If it's 1, it selects its lower input. If it's 0, just like what I'm showing over here in this diagram, if it's 0, it feeds back the cue back into the flip-flop. That means it's acting as an enable, and this is bit number 0, bit number 1, 2, 3, and if it's 1, it will be bringing data from the flip-flop to the left, or for the flip-flop number 3, it's bringing data from serial in. So that's the shift register design. Now looking at this diagram here, we know the full adder, we know the flip-flop, and if you had any doubt about the shift register, this is the structure of the shift register. And the outputs of the shift register are these here. Okay, In this case, it's forming a 4-bit, and then in your case, in the full adder, in the serial adder case, this is going to be an 8-bit. And okay, I'm done with the data path, and now I have to do the controller. What does the controller do? The controller sits and waits for a start. Okay, sits and waits for a start. Remember the state machines. You have a state and sit and wait for a start. Once the start is received, it waits for start to become 0. Actually, what it does is it waits for a pulse on the start. So when it becomes 1, it does not start the process. It just does the initialization. But then when it becomes 0, then the next clock pulse, let's say this is the clock. This is the clock. Okay. When it becomes 0, the next clock pulse starts taking data from A and B. Okay, so if this is the start, this is my A, this is my B input, A in, B in. Starting here, my count begins, and I'm picking up data from A and B and adding them together. So here I'm waiting in state 1 for a start, and state 0 for a start, and I'm assuming that now these signals 1, 2, 3, 4, these signals correspond to these here. Instead of writing all of those in the state, I'm making this notation here. So in the this corresponds to this corresponds to this to this, and this to this. Okay. So in state 0, my ready is 1. I'm waiting for start to become 1. Ready is 1. That means the calculation from the last round is available and it's ready. Okay. And so I keep waiting for start to become 1. As soon as the start becomes 1, my controller says, okay, something new is happening. I'm no longer ready, but let's get prepared. To get prepared, I issue a 1 on, notice a 1 here. I issue a 1 on the init signal. What does the init do? Well, it resets that flip-flop. Okay, so if 1 goes into my data path, it resets the flip-flop, and I'm sure that this is happening. And then I wait for a start to become 0. As soon as the start becomes 0, I go to this state here where my A and B should be added together and should be clocked into the shift register. But then I have, in addition to the shift register that I have to control, as soon as I get into this state, state 2, that I'm prepared, okay, I have to make sure that this state repeats 8 times. Therefore, what I do on this side, I put a counter. I put a counter that as I am initializing my flip-flop, my counter is also initialized. Initialized to 0, 0. Recording.
Okay.
When I come to state 2, 2 things have to happen. State 2. 2 things have to happen. In a state 2, each time with a clock, I have to shift in 1 data into the shift register, 1 bit of data into the shift register. But I also have to keep a count of it. And therefore, I have a counter on the side. The counter on the side gets initialized when my state machine on the left hand side is in state 1. Okay? When I'm in state 2, I start with 0 in my counter. 0, 0, 0. Each time with each clock in state 2, I increment the counter, and therefore I have a signal count enable. Look, count enable, this is the signal over here. Okay? Count enable, that with each clock the count will be going up 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0 until it gets to 1, 1, 1. When it gets to 1, 1, 1, that means I have counted 8 times. The carryout becomes 1. That becomes the complete here. My state 2, though, is waiting for the counter to reach its maximum count, or to reach the completed count. As it is in state 2, as it's incrementing the counter, it is also issuing the shift enable. See this? 0, 0, 1, 1 in state 2. Meaning that it is counting up at the same time it is performing the shifting. This continues until the counter reaches 1, 1, 1. At that point, it knows it has counted enough. It has counted 8 times, and therefore the result must be ready. As soon as this is done, my state diagram or a state machine from state 2 goes into state 0, and then issues ready, waits for next time that start becomes 1. My controller here, even though the circuit is very small, is not all that simple. Actually, my controller is a three-state state machine in which there is an 8-state machine that is activated. Okay. That means when it gets to this last state, S2, a counter, remember counters are state machines also. A counter is activated, and then this state waits in this state until the counter tells it that it has counted. Okay? So I have 2 state machines, one is activated by the other one, and in some controllers you may have even more state machines, but this is a good example of having 2 state machines working hand in hand. Signals issued by my controller are init, shift enable, ready. Okay, and internal control signals. Init, I'm also using it for the counter. Shift enable and count enable. If you look here, this is shift enable and count enable, but shift enable and count enable are the same. Therefore, instead of creating 2 signals, I have 1 signal that I'm using both for count enable and shift enable. Okay, which is okay. I can do that. If you want to generate 2 signals, it's the same thing too. Alright, that becomes my controller. How do I build it? Well, I can build the state machine, the one on the left, using a one-hot implementation, and this is it. 3 states here, S0, S1, S2, S0, S1, S2, and S0 waits for a start. So this is my start. As long as the start is 0, go back to itself. See here, as long as the start is 0, go back to itself. When start becomes 1, go to state 1. When start becomes 1, go to state 1. Wait in state 1 for as long as the start is 1, that means don't go forward, wait for it to become 0, then it start counting. And therefore this is, let's try this here, start equal to 1, and again start equal to 1, keeps looping back. As soon as the start becomes 0, you go into this magic state, state 2, where all the counting and everything is going to be done. And this is start is 0, counting is done, shifting is done, and so on. Okay, this state 2 issues the count enable to my counter. I'll show the counter next. And also issues shift enable to the shifter, okay, which we have seen already here, okay, and waits in this state for completed, and therefore I'm gonna use a different color, completed, for as long as completed is 0. Coming from where? Coming from the counter. Loops back into this. As soon as completed becomes 1. As soon as completed becomes 1, it goes back to the first state, state S0, and then in that state, it again waits for another round. This is this thing here. Okay, and now let's do the counter. Well, we have seen counters before. I'm going to show you a different implementation of the counter. I need a 3-bit counter. I need 3 of these. Okay, and remember that my counter has a requirement that it has to be initialized, because just to make sure that when I'm starting a new round of adding, serial adding, I want to make sure that this begins in state 0, 0, 0. And therefore, in my counter, I have a, in my counter, I have this init signal. That same init signal goes into this and puts the 0 into the counter. This is the way I'm doing the mechanism for the counting. I have 3 of these bits. Just take this, copy it 3 times, and then that becomes a 3-bit counter. The way it works is that if init is not active, that means I have this path active. Okay. This one, if I have a 1 here, that's my carry in actually. If I have a 1 here, this bit is toggling. So 0, 0, 0, the next count is 0, 0, 1. The next count is 0, 1, 0. The next count is 0, 1, 1. The next count is 1, 0, 0. Okay, so you are seeing that the leftmost, the rightmost bit is always toggling. Okay, and therefore you are seeing this exclusive OR coming back into this. The next bit, this one, toggles only if the contents of this bit and the bit on its right hand side are opposite. Therefore, if this is 0, 1, this toggles. If this is 0, 0, 0, okay. Let's see. Alright, so this toggles all the time. Okay, if it's a 0 becomes a 1, if it's a 1 becomes a 0. This next one only toggles okay, here it toggles here, it toggles here, it toggles here. Okay, So it only toggles when it and the bit next to it Okay, this is my counter and see how this works. Actually, the way my counter works is I repeat this structure 3 times. Okay, the way it works is this. Let's look at this. 0, 0, 0. I want it to count to 0, 0, 1. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. 0, 0, 1, I want to count it to 1, 0, 1, 0. This one, I want to count it to 0, 1, 1. 4. 4 becomes 5. 5 becomes 6. 6 becomes 7. 7 becomes 0. Roll over. Okay, so this is my C2, C1, C0 count. C2 plus, C1 plus, C0 plus. Okay? Let's look at the first bit. The first bit, if I have a 1 here, and let's say init is 0, okay? If I have a 1 here, the first bit goes through this XOR, comes back here, that means toggles all the time. Well, of course, it toggles all the time. So the first bit, 0 becomes a 1, 1 becomes a 0, 0 becomes a 1, 1 becomes a 0 with the clock. Okay, so I'm done with the first bit. The second bit, which is sitting here, okay, takes this input and puts this input, into its XOR, okay, into its XOR, and then it toggles only if this is 1. In what condition this is 1? But this the condition that makes this 1 is the condition that makes this one is that I have a 1 on this right hand side input, which is actually the carry in, and also I have a 1 on my C0, and therefore if there is a 1 here, I'm going to show it with a different color. Okay, if there is a 1 here, this one toggles. If there is a 1 here, this one toggles. 1 becomes a 0, 0 becomes a 1, 0 becomes a 1. If there is a 1 here, 1 becomes a 0. The third bit toggles only if all bits on its right hand side are 1. That means the end of the bit number 0 with bit number 1 and this carry in, if all of them are 1, then bit number 2 is going to toggle. I'm going to show that using still another color. Say this one only toggles when there is a 1 here, there is a 1 here. This one only toggles from 1 to 0 when there is a 1 here, there is a 1 here. Okay? And therefore putting 3 of these next to each other gives you a 3-bit counter. It gives you a carry in that you have to set to 1. It gives you an init signal that you reset it to 0. Also, the very last output from the third bit, the AND gate, is the carry out, which you're treating it as completed. Okay, which is completed, that comes here, which is the completed, that comes here. All I do now is I have this done. I have this done. I take 8 of these, build this. I know how to do this. I know how to do this. And then I put the data path with all the 3 components, the controller with those, with the counter and state machines together. That gives me my serial adder. All right, I'm done with the presentation of logic design concepts. At the very end, we did a fairly small example, but a very good one, one that included a lot of things that we have discussed. We talked about gates. We talked about number system. We talked about gates. We talked about transistors forming gates, combinational circuits, Carnot maps, synthesis of combinational circuits using Carnot maps, Boolean algebra, and then we talked about sequential circuits using flip-flops, and then we talked about buses, memories, and RT-level complete design flow. Okay, so in a way, we started with a transistor. Okay, we had number system. Then we started with the transistor. Went to gates. Went to some adders, subtractors. And then from gates, we went into flip-flops. And then we went into counters, shift registers. At the same time, we went into state diagrams. Okay. And then we said that putting together these components gives you the data path. Putting together these components gives you the controller. And then finally, putting together all of these gives you the complete RT level design. Thank you.